Okay, so remember that all atoms want to be stable like the noble gases. That is, they want, for the most part, 2 electrons in their first shell and 8 in subsequent shells. Okay, so this whole 8 electrons in the other shells, it's a little bit of a lie. Okay, but it's a lie we're going to tell you for this year. So we're just going to assume that every shell is full at 8 electrons, except for the first shell, which is 2, and then 8 afterwards. We know this from doing the Bohr-Rutherford diagrams. So if we do a couple of Bohr-Rutherford diagrams really quick, if you take a look at your periodic table, so remember protons, electrons, and neutrons, that's how you figure out what a Bohr-Rutherford diagram is for a given element. So helium has 2, 2, and 2. So our Bohr-Rutherford diagram should look something like this. Okay, so this guy is happy with his 2 electrons on the outer shell. Okay, neon, again, taking a look at your periodic table. So the atomic number is 10, which means that the protons are 10. The electrons are 10. The atomic mass is 20, right? We always round, so it's 20 which rounds to 20. Okay, so that means that mass minus protons gives us neutrons, so 10. Okay, 10, 10. Our nucleus, first shell, and outer shell. So beautiful. Okay, so all of the elements want to have this complete outer shell. And they can do that, they can achieve that goal by either transferring or sharing electrons. Okay, so to complete a valence shell, other elements can transfer or share electrons, other elements being not noble gases. Okay, so if we take a look at lithium and oxygen, so for lithium and oxygen to become stable, they have to exchange electrons to produce the compound Li2O. We're going to draw a Bohr-Rutherford diagram of that exchange. Okay, so let's start by drawing. So you should know from grade 9 that when you have a compound and you see that little number underneath, that subscript number, that indicates the quantity of atoms present in that compound. Okay, so when we see Li2, that means that there are 2 atoms of lithium in this compound. Okay, so we're going to start by drawing 2 Bohr-Rutherford diagrams of lithium. Okay, so I'm going to get you guys to do that. So go ahead, draw your 3. So you should have 3 Bohr-Rutherford diagrams, 2 lithiums and 1 oxygen. Okay, so you should have something that looks like this. Most people do. So far, that's like step 1, right? So we've got our 3 different atoms drawn in the Bohr-Rutherford diagram style. And now we're going to show the transfer of electrons, right? So remember, the reason why we did all this was because we wanted to figure out how these elements get their valence shells complete by making compounds. So your lithium, does it want to gain or lose electrons? But the issue here is, so the lithium wants to lose electrons, and the oxygen wants to gain electrons. If we take a look at their valence shell, oxygen is missing 2, right? Its valence shell has 6 electrons. It's complete at 8, whereas lithium only wants to get rid of 1. That's why we end up with 2 atoms of lithium, okay? Because what happens is each one of these is going to give their electron to oxygen. Okay, so oxygen is going to go and grab 1 electron from each of these lithium atoms. Okay, so that's how you show the transfer, the exchange of electrons using the Bohr-Rutherford diagrams. Okay, so here, note that it is only the outer shell, more scientifically, the valence shell, that is involved in the exchange of electrons. The inner shell is not involved. Okay, so that's why we use Lewis diagrams instead of Bohr-Rutherford diagrams. Because who wants to sit and draw rings around atoms all day long? Not me. Okay, so how do you make a Lewis diagram? Again, this is probably review. You write the symbol for the element and you put the valence electrons around it. Okay, and it's kind of in the same style as a Bohr-Rutherford diagram, so you should still have kind of like pairs of electrons, but it's just points for the electrons. Okay, so a quick comparison. I'm only going to do one because I think you'll get the picture. I'll do one for both Bohr-Rutherford and Lewis, and then I'll just do Lewis for the other one. So boron, right? Again, we're going to have protons, electrons, neutrons. 5, 5, and 6. All right, Lewis diagram. All right, so we got our Bohr-Rutherford diagram with our nucleus and the electrons on the shells, and you have to watch me draw terrible circles, and we're all drawing terrible circles, okay? That's why we got the Lewis diagram. So we put our symbol in there, B, with our valence electrons around. Okay, so for fluorine, there we go, Lewis diagram. Now, I will say something that is a little bit tricky with Lewis diagrams is that it is a very simple form of doing a diagram, but you really have to know how many valence electrons each element has. Okay, so an easier way to determine the number of valence electrons is to look at the Roman numeral of the group of an element. It is the number of valence electrons. For example, beryllium has 2, carbon has 4, and oxygen has 8. Okay, again, take a look at your periodic table, look at the columns. That will tell you how many valence electrons. Okay, so draw a Lewis diagram for each atom without a Bohr-Rutherford diagram. Okay, so you should have Bohr-Rutherford diagrams that look like this. So nitrogen has 5 valence electrons and calcium has 2. Or sorry, Lewis diagrams, I should say. All right. It's faster, obviously, to draw the exchange of electrons with Lewis diagrams. So we're going to do the same thing we did with the other example of lithium oxide. We're going to do that here with aluminum and fluorine. Okay, so it makes the compound AlF3. So remember, again, we're using the subscripts to determine the quantity of atoms of each type in the compound. And you're going to draw your exchange using Lewis diagrams. Okay, so start with making your Lewis diagrams and then move the electrons around. All right, let's go. Okay. Ooh, those are oops. So remember, we're doing 3 fluorines. Okay. And now we're going to indicate the movement of electrons with arrows from the atom that is going to lose the electrons to the atom that's going to gain them. Okay, so here aluminum is the one that's going to be losing the electrons. So we're going to draw those over here like this, okay? It's not super nice, but you get the point. All right. So this also, we're going to start talking about chemical formula. So chemical formula is this thing right here, that AlF3. That's a chemical formula. Okay, it's a chemical formula for that compound. What we've just done is one way to figure out the chemical formula. If I were to give you like two random elements, I could tell you, find the chemical formula for this ionic compound. And you can do it using your Lewis diagrams. So once you have to basically figure out how many of each atom do I need in order for both of the atoms to have full valence shells. Okay, so here, for example, right, we have aluminum, and we could have started with just one fluorine. So we say, okay, so I've got my one aluminum, it has 3 valence electrons. It wants to get rid of all 3 in order to be happy, right? So if we were to draw just one fluorine, that would only take 1 electron away. So that fluorine that we would have drawn is happy, but the aluminum is still not happy, right? So you have to keep drawing fluorines until all 3 of those valence electrons are gone. So that's one way that we can figure out, okay, what quantities are these things appearing in the compound? How do I write this chemical formula? Okay. You can do this without having to draw Lewis diagrams. So you can figure out what the chemical formula is of a given compound, a given ionic compound, without actually having to draw the Lewis diagrams. The way that you do that is by using ionic charges. Okay. So an ionic charge is the charge that an atom will have if it's stable, or if it's, stable. So remember, we were talking about neutral atoms. Neutral atoms are the atoms that we find on the periodic table, same number of protons as electrons. Stable atoms are atoms that have full valence shells, which means that normally their electrons are no longer equal to their number of protons. They've given some away or gained some. Okay? So if we start with calcium, calcium has how many protons and electrons? Right. How many valence electrons? 2. To become stable, calcium wants to donate or give 2. If it gives 2 electrons, it will have how many protons and how many electrons? That's why it has a charge of 2+. The ionic charge is the charge that an atom will have once it's gotten rid of or gained valence electrons like it wants to. It doesn't change the number of protons. So it just changes the number of electrons. And remember, like, protons are pluses and electrons are minuses. So you can literally just do some math and figure out what the ionic charge is. Okay? What would the ionic charge of nitrogen be? And why? Okay. Right. So nitrogen has 5 valence electrons. Right? So it's easier to gain 3 than to lose 5. Right? So that means it wants to gain 3 to be happy. Okay? So because we're gaining 3 electrons, if you gain something that's negative, right? If you gain debt, that's a bad thing, right? Okay, so the ionic charge is 3-. All right, couple of examples, then we're done. So if I want to find the chemical formula for these 2 things, so I've got calcium and chlorine, and carbon and oxygen. Okay, we're going to focus on calcium and chlorine and not on carbon and oxygen. It's not a good example. Okay, so calcium and chlorine. Calcium will have an ionic charge of what? It has 2 valence electrons, which means it wants to lose 2 electrons. So it's going to have a charge of 2+. Chlorine has 7 valence electrons, which means it wants to gain 1. So it's going to have a charge of 1-. And if it's 1, we don't write the number. We don't write 1, we just write a minus. Okay? All right. So if we think about our Lewis diagrams, right, think about the transfer of electrons. We would be moving. So if chlorine has one, basically wants to gain one, and calcium has two to give away, we're going to need 2 chlorine to satisfy calcium, right? Almost done. Okay, so that means that our compound is CaCl2. CaCl2. Okay. Another way to do it, and this is the last thing, is to actually take these symbols and just drop them down. And that will give us CaCl2. We do like a little crisscross, and then we're done. Good?